The Ulam spiral is not just a pattern. It is a quiet revelation hidden in the heart of arithmetic, discovered almost by accident by the Polish-American mathematician Stanislaw Ulam in 1963. The spiral was born from a moment of boredom during a scientific meeting. As he idly plotted numbers in a spiral on graph paper, he began to notice something unexpected. The idea is deceptively simple. Imagine beginning with the number 1 at the center of a grid. From there, you plot natural numbers outward in a square spiral. 2, 3, 4, and so on, each number spiraling around the last. Then, something curious happens. When you highlight only the prime numbers, a subtle structure begins to emerge. Lines, curves, and diagonals weaving their way across the grid. What began as a casual doodle suddenly hinted at hidden order in the distribution of primes, those mysterious and indivisible numbers that have fascinated mathematicians for millennia. Why do so many primes seem to align along diagonal lines? Why do certain regions of the spiral appear dense with primes, while others remain quiet and empty? The Ulam spiral doesn't provide direct answers, but it invites the question. It reveals, through visual simplicity, that even within what we assume to be the randomness of prime numbers, there may be patterns quietly at play. Some of these alignments can be explained through number theory. Others remain elusive, drifting at the edge of mathematical understanding. No definitive formula emerges to predict where the primes will cluster, or why certain diagonals seem to glow with numerical significance. It is a puzzle, not of chaos, but of whispered structure, waiting just beneath the surface. In a world that often feels ruled by disorder, the Ulam spiral is a gentle reminder. Even in randomness, patterns can emerge, not with fanfare or precision, but with a quiet beauty that defies expectation. It asks us to slow down, to look closer, and to see that mystery can exist even in something as simple as counting. The Ulam spiral does not shout for attention. It does not solve great theorems or unlock ancient truths, but in its humble formation, it reminds us that wonder can lie hidden in plain sight, waiting for a moment of curiosity to bring it to light. And sometimes, in the calm of the night, as the numbers spiral out into the unknown, it invites us to drift alongside them, gently, peacefully, into the patterns of dreams. The gyroid surface, first discovered by mathematician Alan Schoen in 1970, is one of the most visually arresting and mathematically profound minimal surfaces known to geometry. Unlike familiar surfaces that bend and fold around recognizable shapes, the gyroid weaves through space without intersecting itself, forming a labyrinth of continuous curvature that is both complex and effortlessly smooth. At its core, the gyroid is a triply periodic minimal surface, a structure that repeats in 3 dimensions, extending infinitely in all directions without ever retracing its path. It has no straight lines, no sharp corners, and no symmetry planes. Instead, it emerges from the balance of curvature. At every point, it bends in opposing directions, so delicately that the overall surface area remains as small as nature will allow. What makes the gyroid particularly fascinating is that although it is a product of pure mathematics, it appears in the natural world, in the microscopic architecture of butterfly wings, in the self-assembling patterns of certain surfactants, even in the nanostructures within bones and cellular membranes. Nature, it seems, is drawn to this hidden order, favoring its efficiency, its symmetry, its quiet elegance. But the gyroid also presents a paradox of perception. It is deeply symmetrical, yet its lack of mirror symmetry makes it feel organic, almost alive. It appears ordered, yet endlessly unpredictable. As your eyes follow its flowing channels, the surface never quite reveals a pattern you can hold on to. You are drawn into a visual puzzle that shifts with every angle, a reminder of how deeply space can be folded, how geometry can conceal depth within simplicity. In physics and materials science, the gyroid holds promise. Its unique topology lends itself to photonic crystals, materials that can bend light in unusual ways. It has been used to design metamaterials, substances with properties not found in nature, like negative refractive indices or tailored acoustic responses. The gyroid, born in abstraction, has become a bridge between theory and application, between what is imagined and what is real. But beyond its utility, the gyroid invites a deeper question. Can a structure be infinite, yet confined? Can something be perfectly balanced, yet in constant motion? It is a surface that exists between contradiction and harmony, curving in upon itself, turning through space with no beginning and no end. To gaze upon a gyroid is to be reminded that beauty in mathematics often lies not in straight lines, but in complexity that flows, in geometry that escapes our expectations. It whispers to us not in equations, but in motion, in texture, in silence. The gyroid is not merely a surface, it is a meditation on space itself, a structure born from symmetry and subtraction, echoing the quiet elegance that nature builds with, again and again. And in this quiet complexity, we are left with a feeling that perhaps the universe is shaped not by lines, but by curves, folded softly, endlessly, beautifully, into itself. The Reuleaux Triangle is a shape that seems to defy our everyday expectations about geometry. At first glance, it may resemble a simple triangle with rounded sides, but it is far more than that. It is a shape of constant width, meaning that no matter how it is turned or rotated, the distance across it from one side to the other remains exactly the same. Unlike the perfect circle, whose constant width is intuitive, the Reuleaux Triangle achieves this same property not through smooth curves alone, but through an elegant tension between arc and corner, between symmetry and surprise. It is built from 3 arcs, each centered at the vertex opposite the side they span. The result is a figure that rolls smoothly, just like a wheel, even though it is not round. This unexpected behavior reveals something deeper, something counterintuitive about shape and motion. We often associate rolling with circles, and constancy with perfection, but the Reuleaux Triangle shows us that other paths to symmetry exist, paths that are no less precise, and no less beautiful. The shape has been used in mechanical designs, in coins, and even in architecture. British 20p and 50p coins, for instance, are shaped with similar curves, allowing machines to recognize them regardless of orientation. But the appeal of the Reuleaux Triangle goes beyond function. It whispers to us of a hidden geometry, one where our assumptions are gently challenged. What does it mean for something to be symmetrical, to be balanced, or even fair? And what does it mean to roll without being round? In a way, the Reuleaux Triangle is a quiet paradox, one that doesn't shout, but softly unsettles. It reminds us that not all that is consistent needs to be uniform, and not all that is perfect must be circular. In this shape we find harmony not through simplicity, but through an unexpected subtle complexity. Like the deepest questions in mathematics, or the most profound truths in nature, the Reuleaux Triangle reveals its wonder only when we take a moment to look more closely, to feel its form, to follow its curve, and to imagine the infinite possibilities hidden in the geometry of things that at first appear ordinary. It is perhaps a lesson that beauty often lies not in what is obvious, but in what quietly subverts our expectations. The superellipse is a shape that exists between worlds, neither entirely a circle, nor strictly a rectangle. It is a smooth, elegant curve defined by a simple mathematical equation, yet its implications stretch across geometry, design, and perception. Also known as the Lemay curve, the superellipse was first studied by Gabriel Lemay in the 19th century, but it would find new life in the hands of the Danish polymath Piet Hein, who introduced it to the modern world not merely as a mathematical curiosity, but as a philosophy of form. At its heart, the superellipse is a generalization of the ellipse. While an ordinary ellipse is defined by a fixed sum of distances to 2 focal points, the superellipse is governed by an exponent. When that exponent equals 2, the result is an ellipse, but when the exponent increases, say to 3, 4, or 5, the shape begins to square off. It forms a figure that seems both organic and geometric, softly rounded, yet boldly structured. This shape gained prominence when Piet Hein proposed it for the design of a public square in Stockholm. He saw in it a reconciliation of opposites, the harshness of the rectangle softened by the grace of the curve. The superellipse allowed architecture to echo the natural world, while retaining the logic of geometry. It became a blueprint for harmony, between rigidity and fluidity, between precision and beauty. But the superellipse is more than a visual form. It is a reflection of the idea that mathematics can describe transitions, not just destinations. Between a circle and a square lies a continuum, and the superellipse reveals that continuum in stunning clarity. It demonstrates that the boundaries we imagine between categories are often far more flexible than we believe. In a deeper sense, the superellipse invites us to reconsider how we define perfection. Is the ideal form always the most symmetrical, the most familiar, or can it be something more nuanced, more adaptable, The superellipse suggests that there is beauty in balance, not extremes. It draws no sharp lines, yet defines space with certainty. As we observe its contours gently bulging, precisely contained, we are reminded that geometry is not only about structure, but also about sensation. Shapes can evoke feelings. Curves can calm. The superellipse does not demand attention. It invites contemplation. It is a quiet rebellion against the binary, against sharp edges and strict categories, and a celebration of the in-between. In the end, the superellipse is not merely a mathematical figure. It is a visual metaphor for compromise, elegance, and possibility. Like the great paradoxes of science, it reminds us that the universe is not confined to what we expect. It bends, it transitions, and sometimes, just like the superellipse, it surprises us with forms we never thought to imagine. The Julia set is one of the most enigmatic and beautiful structures in mathematics, lying at the crossroads of complexity and simplicity. Named after the French mathematician Gaston Julia, these intricate shapes arise from the repetition of a deceptively simple equation in the realm of complex numbers. But like many ideas in mathematics, what appears simple on the surface gives way to a universe of infinite detail. At the heart of a Julia set is a process. Take a complex number, feed it into an equation, and repeat over and over again. With each repetition, or iteration, the number either spirals outward toward infinity, or it remains trapped, orbiting within a bounded region. This dichotomy, between escape and entrapment, defines the structure of the set. What makes Julia sets so mesmerizing is their infinite variation. Every point in the complex plane can seed a different Julia set. Some bloom into fragile dust-like structures. Others curl inward, like ocean waves, or unfurl like fern leaves. Some are fragmented and chaotic. Others are smooth and serene. Each one is a fingerprint of a mathematical reality, singular, precise, and endlessly deep. And yet there's a deeper layer. These shapes are not only beautiful, they are fractals, meaning they contain echoes of themselves at every scale. Zoom in on a Julia set, and you will find the same patterns repeating again and again, smaller and smaller, as if the shape is whispering its own name through infinity. But perhaps what is most compelling is that Julia sets sit on the edge of chaos. They are born from equations that straddle order and disorder, revealing the tension between stability and unpredictability. Slight changes in the initial conditions, a small adjustment to a number, can lead to wildly different outcomes. In this way, Julia sets are a meditation on sensitivity, on how delicate the boundary is between harmony and chaos. They remind us that beauty can emerge not only from symmetry, but also from turbulence. That complexity, when approached with patience, can yield extraordinary insight. The Julia set is not just a shape, it is a window into the nature of iteration, structure, and the infinite. It asks us to look closer, not once but endlessly, because every layer reveals something new. It is a quiet, unfolding universe encoded within numbers, a reminder that even the most abstract equations can give rise to patterns as intricate as lace and as profound as a starfield. As we drift gently between these geometric dreams, the Julia set offers a moment of stillness, a glimpse into how the universe might organize itself, not through chaos or order alone, but through the delicate balance of both. The Mandelbrot set is one of the most beautiful and mysterious patterns ever discovered in mathematics. At first glance, it appears simple. A dark, rounded shape surrounded by delicate swirls and luminous spirals. But beneath this quiet surface lies an endless universe of intricate detail, one that seems to go on forever. It was brought to public attention in the late 20th century by the mathematician Benoit Mandelbrot, whose work revealed how something as simple as a repeating rule could give birth to unimaginable complexity. This discovery didn't just change mathematics. It gave us a new way of seeing patterns, not only in numbers, but in nature, in clouds, in coastlines, in galaxies. What makes the Mandelbrot set so captivating is that it is never finished. No matter how far you zoom into its boundary, you'll find new structures, each one echoing the overall shape, but never quite repeating it. You might see tiny versions of the original form, tucked away in quiet corners, spiraling into infinity. They emerge like whispers in the darkness, recognizable, yet transformed, endlessly unique. There's something deeply calming about this idea, that within what seems like chaos, there is an underlying order, that the complexity of the world, with all its unpredictability and noise, might still be rooted in something profoundly consistent. People often describe the Mandelbrot set as a fractal, a shape made of smaller copies of itself, but it is more than a mathematical term. It feels like a reflection of the universe itself. Whether you're looking at the branching of trees, the spirals of seashells, or the structure of storms, echoes of this pattern seem to be everywhere. It also touches something more philosophical. It reminds us that even from the humblest beginnings, the most extraordinary beauty can unfold. That with time, patience, and perspective, we can begin to see how everything connects, how even the tiniest shift at the edge can ripple endlessly through space. Looking into the Mandelbrot set is like gazing into a dream. It is still yet alive, finite in form, yet infinite in detail. It invites you to slow down, to breathe, and to wonder. As your eyes trace its curves and spirals, you may find your thoughts drifting into the same quiet rhythm. A rhythm that speaks not just of mathematics, but of something deeper, something timeless. And perhaps, in this moment of reflection, the boundaries between numbers and nature, logic and beauty, begin to blur, until all that remains is the feeling of falling gently into the infinite. The fractal fern, often associated with the work of mathematician Michael Barnsley, is one of the most elegant and visually arresting examples of self-similarity in mathematics. At first glance, it resembles a real fern, delicate, branching, and natural. But beneath its seemingly organic form lies a deep mathematical truth: recursion, the repetition of a simple rule, unfolding endlessly. Unlike traditional geometry, which relies on lines, angles, and planes, the fractal fern is born from an iterated function system, a collection of mathematical transformations applied repeatedly. Each transformation bends, scales, and shifts a point in space. When repeated millions of times, this process doesn't yield chaos, but rather astonishingly order. The result is a shape that looks remarkably like a fern leaf, composed of countless smaller copies of itself, each echoing the whole. This recursive structure is not just a mathematical curiosity. It mirrors patterns we observe in nature. In real ferns, coastlines, clouds, and river networks, we find similar patterns repeating across different scales. The fern then becomes more than just a symbol of beauty. It is a window into how complexity arises from simplicity, how the vast intricacy of nature might emerge from a few fundamental rules. But what makes the fractal fern so mesmerizing is not only its form, but what it represents: infinite complexity born from finite instructions. It suggests that there may be hidden laws underlying the natural world, subtle symmetries quietly organizing the chaos we perceive. The fern's recursive unfolding raises profound philosophical questions. If such natural beauty can be generated by mathematical processes, might the very fabric of the universe be written in code? Does the repetition of simple patterns suggest that nature itself is an expression of an underlying algorithm? And yet, for all its precision, the fractal fern invites emotion. There is something soothing, almost meditative, about its gentle repetition, each leaf unfurling into smaller leaves, each part holding the memory of the whole. Like breathing, or waves upon a shore, its rhythm is both infinite and familiar. In this way, the fractal fern speaks to both sides of the human experience, the analytical and the intuitive, the structured and the serene. It reminds us that in the midst of complexity, there is still calm, that in an ever-changing world, some patterns remain eternal. The fractal fern is not merely a mathematical construct. It is an invitation to see harmony where we expect disorder, and to recognize that even the most intricate forms may be governed by remarkably simple laws. It is a leaf that never ends, a whisper from nature and mathematics alike, reminding us to slow down and observe. The asteroid curve is a shape of quiet symmetry, compact, smooth, and deeply harmonious. At first glance, it appears as a soft, four-pointed star, but linger a little longer, and you begin to sense something more, an underlying rhythm, a balance between movement and rest. This curve has its roots in a simple idea. Imagine a small circle rolling inside a larger one, and watching how a single point on its edge traces a path. The result is the asteroid, a closed, looping figure made entirely of gently curved edges and pointed cusps. There is no beginning and no end, just an unbroken seamless flow. What makes the asteroid especially compelling is the way it blends fluidity with structure. Each of its 4 points is a place where the curve seems to pause, almost catching its breath, before continuing its gentle sweep. These points, known as cusps, mark perfect moments of alignment, where tension and release, motion and stillness, meet in harmony. You might find echoes of the asteroid in unexpected places. The reflection of light inside a circular mirror, the tension patterns in stretched materials, or even in the quiet artistry of certain architectural forms. Wherever it appears, it suggests not complexity for its own sake, but simplicity refined into elegance. There is something deeply calming about the asteroid. It reminds us that motion doesn't have to be chaotic, and structure doesn't have to be rigid. In its balanced repeating rhythm, it whispers a kind of mathematical serenity, a shape that moves, but never strays. In a world that often feels rushed and restless, the asteroid curve invites us to slow down, to notice the quiet order behind the shapes of things, and to find, within the calm repetition of form, a moment of still wonder. The cardioid, named from the Greek cardia, meaning heart, is a shape that arises not from sentiment, but from the elegant logic of geometry. At first glance, it resembles the familiar curve of a heart, a shape so often associated with emotion. But beneath its simplicity lies a surprising mathematical richness, one that reveals itself in sound, in light, and even in the orbits of celestial mechanics. At its core, the cardioid is generated by tracing a point on the circumference of a circle, as it rolls around another circle of equal size. The result is not just a curve, but a story of symmetry and transformation. What begins as motion becomes pattern. What begins as rotation becomes resonance. The cardioid is one of the simplest members of a family of curves known as epicycloids, and yet it has captivated mathematicians, physicists, and artists alike for centuries. One of the most intriguing aspects of the cardioid lies in its relationship with reflection. In acoustics and optics, the cardioid emerges again, not as a path traced by a point, but as a pattern of response. A cardioid microphone, for instance, captures sound primarily from the front, while minimizing noise from behind, its pickup pattern reflecting the precise geometry of the curve itself. Similarly, in reflective surfaces, such as a circular mirror, light emitted from a point source can reflect to form a cardioid pattern, a phenomenon as beautiful as it is exact. But the cardioid does not remain confined to the abstract. It appears in the caustics of coffee cups, those bright shimmering shapes that glimmer at the bottom of a cup of lighted liquid. These aren't random. Their geometry made visible. The cardioid emerges again, not as a theoretical shape, but as the footprint of light itself. In complex analysis, the cardioid takes on an even more profound role. As the boundary of the main bulb of the Mandelbrot set, it marks the frontier between stability and chaos, between predictable repetition and infinite divergence. Here, the cardioid is no longer just a curve, but a boundary that defines the limits of order in a fractal universe. The cardioid invites us to consider how simple processes, rotation, reflection, resonance, can give rise to forms of astonishing beauty and precision. It reminds us that even within the constraints of pure mathematics, there is space for shapes that echo the forms of nature, the structures of light, and the rhythms of the world around us. Much like the paradoxes of quantum physics, the cardioid draws us into a deeper contemplation of patterns that defy our expectations. It's a curve born from motion, yet frozen in perfect form. It is a heart, not of flesh and feeling, but of symmetry and structure, a shape that gently whispers of order hiding just beneath the surface of the everyday. In the quiet logic of its curve, the cardioid holds a promise that beauty and understanding are not separate paths, but one and the same, traced softly across the canvas of the cosmos. The Cassini Oval is a curve of subtle beauty and deep mathematical intrigue. First studied in the 17th century by the astronomer Giovanni Domenico Cassini. At first glance, it resembles an ellipse, or perhaps a pair of droplets, gently poised in space. But its true nature is defined not by symmetry alone, but by a quiet principle of distance. Whereas an ellipse is formed by the sum of distances to two fixed points, called foci, the Cassini Oval follows a different rule. For any point on the curve, the product of its distances to two fixed points is constant. It is a slight but profound variation, and from that small change emerges an entire family of shapes, smooth loops, peanut-like forms, and even disconnected ovals, depending on how far apart the two foci lie. This mathematical curve was not just a curiosity. Cassini proposed it as a model for the orbits of celestial bodies, at a time when the true nature of planetary motion was still under fierce debate. Though Kepler's ellipses would ultimately prevail in astronomy, the Cassini oval remains a symbol of the imaginative paths that mathematical ideas can take. Its structure is delicate, and yet defined with precision. As the distance between the foci increases, the oval gradually splits apart, like a shape in quiet contemplation, separating into two mirror images. It's a reminder that simple rules can lead to surprising transformations, and that even in geometry, continuity is not guaranteed. But perhaps the most fascinating quality of the Cassini oval is not just what it shows, but what it suggests. That by slightly altering a condition, we open a portal to a completely new world of forms. That beauty in mathematics as in nature often lies not in perfection, but in variation. And so the Cassini oval invites us to slow down and observe the graceful tension between unity and separation, between order and change. It is not merely a line traced in space. It is a meditation on how we define connection, and how even in geometry relationships can shift, dissolve and reform in endlessly intriguing ways. The deltoid curve, also known as a tricuspid, is a lesser-known but deeply elegant shape in the world of classical geometry. It is not a curve that often finds its way into textbooks or popular discourse, and yet, it possesses a symmetry and motion that is as mesmerizing as it is mathematically profound. This curve emerges from a simple yet surprising construction. Imagine a circle rolling inside another circle that is precisely 3 times its size. Now fix your gaze on a single point on the circumference of the smaller inner circle. As the circle rolls without slipping, that point traces a looping path, sweeping around in smooth cusped arcs. This path is the deltoid curve. Its form is striking, consisting of 3 sharp cusps, or pointed corners, connected by smooth curves. At first glance, it resembles a kind of abstract triangle, but unlike the rigid angular triangles of Euclidean geometry, the deltoid glides between curvature and cusp, its rhythm governed by pure motion. But the true fascination lies not just in its shape, but in what it reveals about symmetry, transformation, and the hidden dance of motion within geometry. Each point on the curve reflects a deeper truth about rotational harmony, how simple constraints give rise to intricate behavior. In the language of complex analysis, the deltoid curve is the envelope of the family of circles tangent to 3 fixed points. In more visual terms, it's a window into the fluid relationship between curves and their generating motions. And just as the EPR paradox invites us to rethink space and time, the deltoid beckons us to reconsider what a path truly is. Not merely a trail on a surface, but the echo of something turning, something circling, something becoming. Curiously, the deltoid curve also has connections to mechanical design. It is found in gear systems and engineering, where it serves as a profile for motion that repeats with elegance and predictability. In this sense, it bridges the abstract and the practical, theoretical beauty made tangible. And yet, despite its symmetry, the deltoid never feels static. There is a quiet dynamism embedded in its very form. Even when drawn, even when paused, it feels as though it is still rolling, still tracing, still alive. Like many mathematical shapes, the deltoid curve serves as more than just a pattern. It is a gesture of the universe, a soft echo of how motion can be sculpted into form. It does not demand understanding. It does not shout for attention. It simply exists, quiet, eternal, and beautifully complete. In watching it unfold, we are reminded of the subtle intelligence beneath geometry, a whisper of order, a looping rhythm, a path, traced not just by a point, but by a principle. And as you drift deeper into the softness of thought, the deltoid curve rolls on, tracing its perpetual cycle in perfect silence. The Nephroid Curve is a quiet marvel in the world of classical geometry, a shape at once simple in form, and yet deeply suggestive of hidden patterns in light, motion, and space. First formally described in the 17th century by the Danish mathematician Ole Rummer, the nephroid is a specific type of epicycloid, a curve traced by a point on the circumference of a smaller circle as it rolls around the outside of a larger fixed circle. But unlike its more symmetrical cousins, the nephroid carries within it a subtle asymmetry, a complex grace that has captivated both mathematicians and physicists for centuries. Its name, derived from the Greek nephros, meaning kidney, refers to its gently lobed heart-like structure. Yet what lies beneath the curve is not biological, but deeply mathematical. It arises from an elegant ratio. When the rolling circle has exactly half the radius of the stationary one, the result is the classic nephroid, a shape with two distinct cusps, gracefully curved edges, and a symmetry that hints at deeper truths. But the nephroid is not just a geometric curiosity. It appears, unexpectedly, in the reflection of light. When parallel rays, like those from a distant source, hit the inside of a circular mirror, they converge and trace a shape identical to the nephroid. In optics, this is known as a caustic, the luminous curve you might see in the base of a coffee cup, or in the shimmer of light beneath a glass. The nephroid becomes a hidden script written by light itself. This connection between pure geometry and natural phenomena lends the nephroid a kind of quiet mysticism. It reminds us that mathematics is not merely a tool for abstraction. It is a language that nature seems to speak fluently, often in places where we least expect it. And yet the nephroid also carries a paradox of its own. It is born from motion, yet frozen in form. It emerges from the simplest of rules, yet expresses a complexity we can neither fully capture nor exhaust. It's a curve that defies our expectation of simplicity, while gently inviting us to reflect on the deeper harmonies embedded in the fabric of space. In contemplating the nephroid, we are reminded softly, silently, that the universe is not only governed by laws, but also composed of patterns. Patterns that are not always visible, but always there, waiting, like the shape of light in a mirror, to be revealed. The helix is one of the most elegant and fundamental shapes in nature and mathematics. A smooth, spiraling curve that winds around a central axis like a climbing vine or coiled spring. It is a form that embodies both motion and symmetry, at once simple in appearance and profound in its implications. Mathematically, a helix is defined as a curve in three-dimensional space that maintains a constant angle to a fixed axis. This simple condition gives rise to a shape that seems to twist infinitely forward, like time itself. The helix appears in the geometry of corkscrews, the paths of subatomic particles in magnetic fields, and the very structure of DNA, the blueprint of life. But the helix becomes even more captivating when it doubles, when one spiral is mirrored and entwined with another. This is the double helix, most famously seen in the molecular structure of deoxyribonucleic acid, or DNA. In 1953, James Watson and Francis Crick described this shape not merely as a chemical structure, but as a revelation life itself encoded in a winding ladder of information. Each strand of the DNA double helix curves gently through space, joined by rungs of paired molecules, adenine with thymine, cytosine with guanine, bonded across the divide like a silent handshake between threads of life. The spiral is not just elegant, it is efficient, compact, and remarkably stable, able to coil meters of genetic code into the microscopic nucleus of a single cell. But why the spiral? Why not a straight line, or a zigzag? Nature seems to prefer the helix, because it balances structure with adaptability. A helical shape can stretch, compress, and twist without breaking, qualities that make it ideal not only in biology, but also in architecture, engineering, and design. From the curvature of galaxies to the tendrils of climbing plants, the helix reveals a universal pattern, a geometry that binds the microscopic and the cosmic. And yet beyond its physical structure, the helix invites metaphor. It suggests growth, evolution, and continuity. A spiral is a path that never quite repeats itself, yet it always returns close to where it began. It is a visual rhythm of expansion, a journey that moves forward by circling inward. In the double helix, we find something even more profound: duality and unity, a dance between two strands that never touch but are forever intertwined. It is a reminder that complexity can arise from simplicity, that beauty often lies in the balance between tension and harmony. As we drift further into thought, or into sleep, the helix continues to spiral, quietly and eternally, a shape born of pure mathematics, yet written into the code of every living thing, a silent, graceful curve that, like the questions of the universe itself, turns forever forward. The Trefoil Knot is the simplest non-trivial knot in the field of topology, an elegant loop that crosses over itself in a threefold symmetry, forming a single, unbroken strand that twists through space in a way that seems both orderly and defiant of linear logic. At first glance, the trefoil appears deceptively simple. A smooth curve looping over and under itself just once in each direction. But beneath this simplicity lies a profound complexity. Mathematically, it is classified as a 3-2 mitros knot, meaning it wraps around the surface of a torus once through the hole, and twice around its body before closing on itself in a seamless circuit. What makes the trefoil so captivating is not only its shape, but what it reveals about the deeper structure of space. Unlike a simple loop, the trefoil cannot be untied without cutting the strand. It is fundamentally knotted, an intrinsic property that cannot be removed through any amount of twisting, stretching, or reconfiguring. In this sense, the trefoil becomes more than a shape. It becomes a topological invariant, a signature of entanglement in three-dimensional space. In the physical world, trefoil-like structures appear in DNA loops, in fluid vortices, even in the magnetic fields of solar plasma. Nature seems to favor such efficient and tangled configurations, not because they are convenient, but because they represent states of balance between constraint and flow. In mathematics, the trefoil is more than just a curious knot. It plays a key role in knot theory, a field that intersects with quantum field theory and string theory, where the fabric of reality itself may be composed of vibrating knotted loops. Remarkably, the trefoil is chiral asymmetric. It exists in both left and right-handed forms, or mirror images that are fundamentally non-superimposable. This property, known as chirality, echoes throughout chemistry and biology, from the twisting of amino acids to the geometry of entire molecules. But beyond its physical manifestations and mathematical classification, the trefoil knot invites us into a more abstract reflection. It suggests that complexity does not always arise from multiplicity, that even a single continuous strand can form a system that is both bounded and infinite in meaning, that within even the most modest structures, there may be hidden intricacies, twists of logic and loops of consequence, that resist simplification. In its silent looping rhythm, the trefoil knot reminds us that not all entanglements are meant to be undone. Some are meant to be studied, appreciated, and perhaps even revered as quiet metaphors for the paradoxes of life, the hidden connections that bind us, and the beautiful complexities we cannot always unravel. As you watch this form slowly rotate, softly shimmering against a calm, infinite background, consider this: the trefoil knot is not just a puzzle or a pattern. It is a symbol of continuity without repetition, of unity through complexity, of a universe where even the simplest path can lead through the most unexpected turns. The Reuleaux Curve, sometimes known by its poetic name Rhodonia, is one of the quiet wonders of geometry, a shape that seems to blossom effortlessly from the heart of mathematics. At first glance, it resembles a flower, delicate, symmetrical, endlessly unfolding, and yet it is not drawn by hand or inspired by nature's whim. Instead, it emerges from a precise and subtle process, a dance of points spinning in harmony, tracing arcs that open like petals on a still morning. Each curve is unique. Some form 3 petals, others grow into 5, 7, or a dozen, and as the curve gently loops back toward itself, it gives the impression of motion without movement, of blooming without time. It is not animated, and yet it breathes. What makes the Reuleaux Curve so captivating is not just its resemblance to nature, but its refusal to be confined by it. Unlike a real flower, it does not fade. It doesn't weather with the seasons or depend on sunlight to exist. It floats timelessly, abstract and unchanging, in the space where imagination meets design. But perhaps its beauty lies in its contradictions. It is both orderly and organic, rigid yet soft, mechanical yet emotional. It looks simple, and yet behind every swirl is a quiet intelligence, a silent structure waiting to be noticed. The Reuleaux Curve invites no urgency. It asks for no conclusions. It simply offers its shape, its soft petals spiraling inward and outward, like a visual lullaby, repeating just enough to feel familiar, but never so much as to grow dull. And maybe that's why we're drawn to it. Because in a world filled with noise and motion, the Reuleaux Curve holds still. It reminds us that there is grace in stillness, that repetition can be restful, that not all beauty needs explanation. It is a shape that does not shout, but whispers. A shape that does not try to be more than what it is, and in doing so becomes something more than we expected. The Conchoid Curve is one of the lesser-known, yet deeply captivating shapes in the world of classical geometry. Its name, derived from the Greek word conchoides, meaning shell-like, is a quiet nod to its smooth, undulating form, reminiscent of a seashell or a wave captured in stillness. First studied by the ancient Greek mathematician Nicomedes in the 3rd century BCE, the conchoid was originally constructed as a tool to solve a problem: how to double the cube or trisect an angle. Tasks known to be impossible with only a straight edge and compass. Yet, in seeking a practical solution, Nicomedes uncovered a curve that would endure not only for its utility, but for its beauty. At its heart, the conchoid curve is defined by a simple idea. Imagine a fixed point, a beacon in space, and a straight line. Now, from every point on that line, draw a segment that extends a fixed distance away from the point, and toward or away from the fixed point. The tip of each segment traces a new curve, the conchoid. This process, though mechanical, yields something organic. The resulting shape often features a delicate inward cusp, like a fold in fabric or the bend of a petal, revealing that even from rigid construction, fluidity can arise. The curve may be single-lobed or double-lobed depending on the configuration, sometimes open, sometimes forming a soft and closed loop. But the intrigue of the conchoid curve goes deeper than its silhouette. It challenges our intuition about distance, straightness, and direction, reminding us that the act of stepping away from a boundary, while holding to a fixed rule, can generate entirely new forms of order. In a sense, it mirrors how structure and deviation coexist, how constraints can give birth to unexpected elegance. Over centuries, mathematicians revisited the conchoid in different guises, studying its reflective properties, its intersections, its role in optics. In some configurations, it behaves like a lens, bending light toward a focus, concentrating energy through space, like nature does in the curvature of a leaf or the cornea of an eye. And yet, beyond the mathematics and mechanics, the conchoid evokes something quietly human. We are, after all, beings of fixed points, anchored to our histories, our identities, yet constantly extending ourselves outward, tracing arcs shaped by intention, by limit, by the pursuit of meaning. The conchoid curve becomes a metaphor not only for spatial relationships, but for the way we navigate between constancy and change. Like the EPR paradox, it asks us to reconsider simple assumptions, that a point, a line, and a rule might only create the obvious, but instead, they open the door to something new, unexpected, delicate, and profound. In the conchoid, we find not just a solution to a classical problem, but a quiet expression of the geometric imagination, structured, mysterious, and endlessly unfolding. Delaunay triangulation is a geometric construction that at first glance appears deceptively simple, just a way of connecting points into triangles. But beneath its quiet elegance lies a powerful principle of spatial harmony, one that reflects a deeper order within randomness. Named after the Russian mathematician Boris Delaunay, who introduced the concept in 1934, this triangulation begins with a scattered collection of points, unassuming, disordered. Yet from this apparent chaos, a network emerges. Each triangle is formed in such a way that no point lies inside the circumcircle of any other triangle. This simple condition leads to something remarkable, the most balanced and efficient triangulation possible. In a world where shapes often seem arbitrary, the Delaunay triangulation finds the configuration that maximizes the smallest angles, avoiding narrow, skewed triangles in favor of those that feel evenly spread and stable. It's a principle of fairness and geometry, where each connection seems to honor the space between its neighbors. But what makes this pattern especially beautiful is not just its symmetry, but its adaptability. Whether on flat planes or curved surfaces, in natural phenomena or computational algorithms, Delaunay triangulations adjust with seamless intelligence. They are found in the tessellation of geological formations, in the way insects build their eyes, and in the very algorithms that simulate cloth, fluids, and motion in computer graphics. And yet, beyond its technical utility, the Delaunay triangulation offers something more, an aesthetic of cohesion, like veins branching through a leaf or the layout of constellations in the night sky. It hints at an unseen rule of balance that governs both the organic and the abstract. It asks a quiet question: how can structure arise from randomness? How can simplicity give rise to beauty? As we follow its lines and angles, we are reminded that order is not always imposed from above, but can emerge gently, almost invisibly, from within. And in that silent unfolding of connections, the Delaunay triangulation becomes more than a geometric tool. It becomes a metaphor for harmony and complexity, for calm within chaos, and for the quiet intelligence of space itself. Voronoi diagrams are a quiet mathematical way of dividing space, a tapestry of boundaries defined not by walls or roads, but by the simple notion of proximity. Named after the Ukrainian mathematician Georgy Voronoi, these diagrams reveal a hidden order beneath randomness, carving the plane into regions, each belonging to a single point, or what we might call a seed. The logic is elegantly straightforward. For each seed we draw a region consisting of all the points that are closer to it than to any other, and yet the results are anything but mundane. The diagram blooms into a network of jagged cells and fractured symmetry, each one forming organically, like the cracked surface of parched earth, or the cells in a dragonfly's wing. At first glance, these regions might seem arbitrary, but look deeper and you begin to see something more profound. An algorithmic fairness, a mathematical democracy, where every point in space quietly declares its allegiance to the nearest center. This idea, so simple in principle, finds itself echoed in fields as diverse as meteorology, astronomy, biology, and urban planning. In nature, Voronoi patterns emerge in places untouched by human design. The structure of soap bubbles, the tessellation of giraffe skin, the distribution of seeds in a sunflower, each a soft whisper of geometry's presence in the natural world. In these forms, there is no leader, no guiding hand, only proximity, pressure, and equilibrium. Yet the result is one of striking beauty and remarkable efficiency. But Voronoi diagrams don't merely depict what is, they also suggest what could be. In their abstraction lies a metaphor for influence, for territory, for interaction. They ask, how far does one's presence extend? When does another's begin? What space is truly ours? And how do we define the boundaries between us? And like so many ideas in mathematics, Voronoi diagrams straddle the boundary between the visible and the hidden, the constructed and the emergent. They remind us that structure can arise from simplicity, and that even in apparent chaos, order is always nearby, quiet, precise, and waiting to be revealed. To fall asleep to such a thought is to imagine the world gently dividing and recombining itself, like ripples in a pond, or stardust settling into celestial neighborhoods. In the geometry of space, even distance has a shape. The harmonograph is a mechanical apparatus, simple in construction, yet profound in the beauty it reveals. Using a system of pendulums, it traces delicate flowing curves on paper, shapes that are both precise and organic, chaotic yet serene. These figures are not drawn by human hand, but rather by the quiet logic of physics, gravity, motion, and time, interwoven. At its core, the harmonograph is governed by the principles of harmonic motion. Two or more pendulums, each swinging with its own rhythm and direction, guide a pen across a surface. The result is a series of looping patterns, slowly fading as friction robs the pendulums of their energy. And yet, in those fading lines, we see a fleeting harmony, patterns that resemble flowers, ripples in water, or even orbits in space. What makes the harmonograph so intriguing is not merely its ability to draw, but the deeper truth it illustrates that complexity can arise from simplicity, that beauty can emerge from constraint. The figures it produces are known as Lissajous Curves, but in the context of the harmonograph, they become something more, something alive. They pulse, twist, and spiral in ways that suggest movement frozen in time. The motion of the pendulums introduces just enough unpredictability to create a sense of wonder. Tiny shifts in length, angle, or phase produce vastly different shapes, reminding us that even in a deterministic system, the outcome can feel infinitely varied. In this quiet dance of mechanics and mathematics, we are invited to reflect, not only on motion, but on balance, on the ephemeral nature of beauty. The harmonograph does not repeat its performance perfectly. Each drawing is unique, impermanent, a singular trace of a moment in time, never to be exactly reproduced again. Like the quantum entanglements of physics, the curves of the harmonograph hint at an unseen connection, a resonance between parts that gives rise to a unified whole. It is as if the pendulums, though swinging independently, are in silent dialogue, producing a shared expression of order. There is something deeply meditative in watching the harmonograph work, in seeing the figure emerge, line by line, arc by arc. It is a reminder that the universe is full of patterns waiting to be revealed, not by force, but by patience, not by control, but but by allowing things to unfold according to their nature. In the end, harmonograph figures are more than just drawings. They are echoes of harmony, fleeting geometries that invite us to listen to the rhythm of motion, to the subtlety of form, and to the quiet mathematics of beauty itself. The hexaflexagon is one of the most quietly astonishing objects in recreational mathematics. A simple strip of paper, folded in such a way that it reveals hidden faces each time it is flexed. At first glance it appears to be nothing more than a hexagon with a few creases, but as you begin to fold and flip its layers, a surprising property emerges. It possesses more sides than it initially seems. Discovered in 1939 by British student Arthur H. Stone, the hexaflexagon was born not from a laboratory or a blackboard, but from the margins of a notebook. Stone had trimmed American paper to fit his British binder, and began folding the leftover strips. What he uncovered was a shape that defied expectation, one that could be turned inward again and again, revealing new faces concealed within the folds of paper. The paradox of the hexaflexagon lies not in quantum mechanics or cosmology, but in simplicity. It appears static, almost trivial, and yet within it hides a system of transformations, faces that cannot be seen unless the object is manipulated just so. One begins to wonder how many faces are there. How many layers remain undiscovered? The answer depends on the structure of the fold itself, but this is more than a puzzle. Like many objects in mathematics, the hexaflexagon is a metaphor, a meditation on hidden complexity beneath apparent simplicity. It is a reminder that even the most unassuming things may hold infinite possibilities, that transformation is often a matter of perspective, and that depth can exist even in a flat plane of paper. The movement of the hexaflexagon feels rhythmic, almost hypnotic. Each fold is a quiet revelation. Each turn invites another, and with each new face we are reminded that geometry, at its most elegant, has the power to surprise, not through complexity, but through the subtle interplay of form, motion, and the unexpected. In watching it flex, we do not simply observe a mathematical curiosity, we glimpse something deeper, a quiet unfolding of order, hidden just beneath the surface. Spirograph patterns are among the most mesmerizing forms ever drawn by simple motion. At first glance, they resemble intricate mandalas or ornate floral motifs, looping with perfect symmetry and gentle curves. But behind their visual elegance lies a surprisingly precise and mathematical structure. The origin of these patterns traces back to the concept of epitrochoids and hypotrochoids, curves formed when a point on a circle rolls around another circle, either inside or outside its perimeter. As the rolling circle moves, the tracing point sweeps out a continuous path, forming spirals, petals, and rosettes that appear to emerge effortlessly from the paper or screen. And yet each loop is determined by exact ratios, by cycles and radii dancing in harmony. What makes spirograph patterns so enchanting is their dual nature, chaotic yet ordered, spontaneous yet predictable. With just a few mechanical rules, they produce an infinite variety of shapes, no two quite the same. They are a visual metaphor for the hidden beauty in motion, where complexity arises from simplicity and symmetry emerges from repetition. The magic lies in their generation. Spirographs embody the idea that geometry isn't always rigid or cold, it can be playful, even whimsical. When we watch a spirograph being drawn, we're witnessing the unfolding of a silent algorithm, one that doesn't rush, but patiently reveals itself over time. And yet there is something deeper. Spirograph patterns remind us that even the most intricate systems can be governed by just a few elegant principles. That beauty doesn't always come from complexity, but from balance, from the relationship between curves, between angles, between rotations. As the lines trace themselves across a surface, looping inward and outward with rhythmic grace, they offer more than just aesthetic pleasure. They invite reflection. Reflection on how patterns exist everywhere, often just beyond the edge of perception. In waves, in sound, in time, in the way planets move and tides shift. To observe a spirograph is to enter a quiet world of motion, where every curve leads seamlessly into the next, and every return to center feels both inevitable and surprising. It is a visual lullaby, a geometry that does not need to explain itself, because it simply is. In this space of gentle curves and endless loops, we are reminded of the calm that arises when chaos finds form. Spirograph patterns don't just entertain the eye, they soothe the mind. They echo a simple truth that harmony can be found in motion, and stillness in repetition, and as each shape slowly unfolds into the next, we are left with a lingering feeling, one of balance, of wonder, and of quiet joy, nestled deep within the turning of circles. Lissajous curves are delicate, hypnotic figures formed by the interaction of two simple sine waves, named after Jules-Antoine Lissajous, the 19th century French physicist, who studied their motion using a beam of light and a pair of tuning forks. These curves are more than just mathematical abstractions. They are echoes of harmony, inscribed in space. At their core, Lissajous curves arise from the intersection of two perpendicular oscillations, one horizontal, the other vertical, each vibrating at its own frequency and phase. As time unfolds, these oscillations trace out graceful loops and arcs, forming figures that resemble ellipses, figure eights, and even intricate knots, depending on the precise relationship between their frequencies. What makes these curves so mesmerizing is their balance between order and complexity. When the frequencies are whole number ratios, the patterns close into elegant symmetric shapes. But as these ratios drift further apart, the curves begin to explore a broader, more chaotic beauty, never quite repeating, yet never truly random. In the classical world, such curves find expression in physical systems, in the vibration of violin strings, in the tracing of a pendulum affected by perpendicular forces, and even in the delicate dance of celestial bodies under competing gravitational pulls. Each pattern tells a story, not of one force, but of two, woven together in time. There is something deeply calming about this duality. Lissajous curves remind us that complexity can emerge from the simplest rules, two oscillations, two directions, and yet an infinity of forms. They invite us to consider how structure emerges not just from stillness, but from motion, how harmony is not the absence of movement, but the synchronized interplay of it, and in that interplay, there is a kind of visual music. One does not merely see a Lissajous curve, one experiences it, like a silent song etched in space, a whisper of mathematics, a trace of rhythm, a frozen moment of resonance. In their looping elegance, Lissajous curves become a meditation, a reminder that beneath the noise of the world, there are patterns waiting to be seen, and in the quiet of those patterns, we find a kind of peace. Escher's impossible cube is one of the most quietly baffling illusions in the world of geometry and visual perception. Inspired by the Dutch graphic artist M.C. Escher, the shape appears at first glance to be a perfectly ordinary three-dimensional cube. Its edges are straight, its angles clean, and its structure symmetrical, until the mind tries to make sense of how the parts connect. What makes the impossible cube so perplexing is not its appearance alone, but the quiet contradiction it harbors within. The cube suggests a coherent three-dimensional form, but upon closer inspection, we see that its beams do not align in any way that a true object ever could. Certain bars seem to pass in front of others and behind them at the same time. The logic of spatial depth collapses. The shape loops into itself, creating a paradox, not unlike the logical puzzles found in mathematics and philosophy, where definitions circle back and logic folds inward. At its core, the impossible cube invites us into a world where perception and reality begin to diverge. Our eyes and brain attempt to impose order, to reconcile the image as something familiar. But no matter how we look at it, the form resists resolution. It lives permanently on the threshold between what seems possible and what can never be built. This illusion was not invented to deceive, but rather to evoke wonder, to suggest that even simple shapes can house impossibilities. Escher's works remind us that our interpretation of space is not always reliable, that what appears solid, certain, and graspable may be nothing more than a projection of the mind. In this sense, the impossible cube mirrors deeper questions in geometry and physics. How do we define dimension? Where does the line between perception and objective reality truly lie? And how often do we mistake internal coherence for external truth? Escher's cube does not offer answers. Instead, it leaves us gently suspended in a state of elegant uncertainty, a quiet reminder that the most familiar forms may contain the most subtle mysteries. It is a shape that defies construction, but not imagination. A cube that cannot exist, and yet, we see it, we know it, and we are fascinated by it. Like a dream that fades as we try to hold on to it, the impossible cube dissolves when reason approaches too closely, and that is its beauty. The Apollonian Gasket is not merely a collection of circles. It is a doorway into infinite recursion, born from the ancient curiosity of Greek mathematicians, and elevated into modern mathematical beauty. Named after Apollonius of Perga, a pioneer in the geometry of conic sections. This fractal pattern emerges from a deceptively simple idea, filling the space between three mutually tangent circles with ever smaller circles, each also tangent to its neighbors. But from this simplicity unfolds a complexity that seems almost paradoxical. As each new circle is inscribed within the curving triangular gaps left by its predecessors, the space grows more intricate, more refined, more impossibly dense. Yet no matter how many circles are drawn, an infinite amount of empty space still remains. The gasket is complete, and yet never finished. At its heart lies a fascinating tension between the continuous and the discrete, between the finite and the infinite. Every circle is real and measurable, and yet their number is without end. The perimeter of the structure grows with every addition, and yet the total area remains bounded. Mathematically, the Apollonian gasket is a fractal, a shape that exhibits self-similarity at all scales. Zoom into any portion of the design, and the same intricate dance of circles appears again and again, like echoes of a perfect form repeating into eternity. What's more, these gaskets are not just abstract constructions, they are governed by number theory, revealing an elegant relationship between geometry and the integers. In some cases, every circle in the pattern has an integer curvature, hinting at a deep hidden arithmetic order beneath the visual harmony. To gaze upon the Apollonian gasket is to witness a kind of mathematical meditation, a structure that is at once calm and endlessly complex. A single glance invites 1,000 questions. How can such order arise from such simplicity? Can infinity be contained within a finite space? Like the EPR paradox in quantum physics, the Apollonian gasket blurs the line between the intuitive and the incomprehensible. It reminds us that beauty in mathematics is not always about answers, but often about the questions that continue unfolding long after the problem is posed. It is a shape that whispers to the curious mind, there is always more to see, and in that whisper, it offers a quiet kind of wonder, perfect for falling asleep and dreaming of the infinite. The Archimedean Solids, named after the ancient Greek mathematician Archimedes, represent one of the most elegant intersections of geometry and harmony. While less well known than the Platonic Solids, they are no less extraordinary. These 13 convex polyhedra, each composed of 2 or more types of regular polygons meeting in identical vertices, occupy a unique space in the landscape of mathematical beauty, structured, symmetrical, and yet more intricate than their Platonic cousins. What makes the Archimedean Solids so fascinating is their balance between order and diversity. Unlike the Platonic Solids, which are built from just one type of regular face, Archimedean Solids embrace variety. Triangles, squares, pentagons, and hexagons combine seamlessly to create shapes that feel both familiar and mysterious, as though nature itself designed them to house secrets. Each Archimedean solid holds within it a kind of geometric rhythm. The truncated icosahedron, for instance, a sphere-like shape composed of 12 pentagons and 20 hexagons, is the very structure of the carbon molecule known as the buckyball, and also the pattern of the classic soccer ball. Others, like the snub cube or the truncated dodecahedron, seem less likely to be found in everyday life, yet their form evokes something ancient, something primordial, like symbols from a forgotten language of the universe. The unifying property among all Archimedean solids is vertex transitivity, that is, each vertex, each point where edges and faces meet, has an identical arrangement of faces. This symmetry gives them a sense of wholeness, a mathematical resonance that is deeply satisfying to the eye and the mind. Archimedes' exploration of these solids over 2,000 years ago was ahead of its time, and it wasn't until the Renaissance that his list of these forms was fully rediscovered and understood. Today they continue to inspire not just mathematicians, but artists, architects, and designers, those who seek forms that are stable, efficient, and beautiful. But beyond their technical definition, Archimedean solids suggest something deeper. They invite us to reflect on the way diversity and symmetry coexist in nature. They are a metaphor for balance, how complexity does not preclude harmony, and how variation can still obey a deeper order. Like the EPR paradox in quantum mechanics, which challenges our understanding of connection at a distance, Archimedean solids challenge our assumptions about structure, about how different elements can combine into something coherent, something that transcends their parts. They are not just shapes, they are ideas made visible, ideas that whisper to us about the nature of form, space, and symmetry in the universe. And in their quiet perfection, the Archimedean solids offer a kind of reassurance that even in a world of complexity, there can be patterns of profound beauty, waiting patiently to be seen. Platonic solids are among the most elegant and symmetrical structures in all of geometry. Named after the ancient philosopher Plato, who believed these shapes were the building blocks of the cosmos, they represent a timeless intersection of mathematics, nature, and philosophy. There are only 5 of them: the tetrahedron, cube, octahedron, undodecahedron, and icosahedron. Each of these shapes is defined by a strict set of criteria. All of their faces are identical regular polygons, all edges are the same length, and the same number of faces meet at every vertex. This perfect symmetry sets them apart as uniquely harmonious figures within 3-dimensional space. The icosahedron, for example, is made of 20 equilateral triangles. It is the most complex of the 5 Platonic solids in terms of its number of faces, yet it maintains the same balanced unified structure. To the ancient Greeks, it represented the element of water, fluid, dynamic, and encompassing. But the significance of Platonic solids extends far beyond classical philosophy. They appear in the microscopic architecture of viruses, in the crystalline structures of minerals, and in the geometry of fullerene molecules, carbon atoms arranged in perfect symmetrical forms. These solids also have profound implications in the realm of mathematics. Their rarity, only 5 exist, comes not from a lack of imagination, but from the constraints of symmetry and regularity. Beyond these 5, no other convex polyhedra can meet all the conditions. This exclusivity lends them an almost sacred quality, as if they are the fundamental codes of spatial order. For Plato, these solids were not merely abstract ideals, they were symbols of perfection, reflections of an underlying truth about the structure of the universe. In the Timaeus, he proposed that the elements of matter themselves were made of these forms: the tetrahedron for fire, the cube for earth, the octahedron for air, the icosahedron for water, and the dodecahedron, to represent the cosmos as a whole. Today we understand that matter is composed of atoms and particles, not perfect geometric solids. Yet the Platonic solids endure, not because they describe the physical world literally, but because they point to something deeper, an enduring sense of order, harmony, and aesthetic perfection. To study these shapes is to engage in a quiet meditation on symmetry. Their balanced proportions and internal consistency offer a kind of stillness, a moment of clarity in an often chaotic world. They remind us that within the vast space of possibility, some patterns emerge with a simplicity so profound, they feel inevitable. And so, the Platonic solids continue to inspire wonder, not only as mathematical curiosities, but as symbols of a hidden architecture underlying space itself. In their quiet perfection, they invite us to imagine a universe where everything fits, where balance is not just possible, but essential. A world built, quite literally, on beauty. The Fibonacci sequence is one of the most quietly elegant patterns found in both mathematics and nature. Named after the 13th century Italian mathematician Leonardo of Pisa, better known as Fibonacci, this sequence begins with the simple numbers 0 and 1. From there, each subsequent number is the sum of the two preceding it: 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. At first glance, it seems like a modest pattern, but its true beauty lies in how often, and how effortlessly, it appears in the world around us. From the spirals of sunflower seeds and pine cones, to the branching of trees and the arrangement of leaves, the Fibonacci sequence governs forms of natural growth in a way that feels both inevitable and profound. When visualized, this sequence takes on a distinct, almost hypnotic form. Squares whose side lengths correspond to Fibonacci numbers can be arranged in a tiling pattern. If one then draws quarter circles through these squares, a spiral begins to emerge, a graceful expanding curve known as the Fibonacci spiral. This spiral, though composed of simple arcs, mirrors a much deeper mathematical form, the golden spiral, which increases in size by a factor of the golden ratio with every quarter turn. The golden ratio itself, approximately 1.618, is found by dividing each Fibonacci number by its predecessor as the sequence progresses. The further along one travels in the sequence, the closer the ratio becomes to this mysterious constant. But perhaps the most intriguing aspect of the Fibonacci sequence is not just where it appears, but why it does. Why should a sequence of numbers first described in a medieval manuscript appear in the growth of seashells, the spirals of galaxies, or the proportions of classical architecture? Some have speculated that this pattern represents an optimal efficiency in natural systems, a way for living things to grow and expand without wasting space or energy. Others see in it something more metaphysical, a hidden order quietly shaping the universe behind the scenes. In the world of art and design, the Fibonacci spiral has often been used to evoke balance and harmony. From the compositions of Renaissance paintings to the structures of sacred geometry, it suggests a proportion that feels intuitively right, neither too uniform, nor too chaotic. And yet, like many profound truths, the Fibonacci sequence is deceptively simple at its core. It begins with nothing, and 1, 0 and unity, absence, and the first spark of something. From there, it unfolds, calmly, recursively, building complexity from simplicity, and revealing order where none seem to exist. It is a quiet reminder that the universe, in all its vast intricacy, may be built from the repetition of small, humble truths, and in that repetition, there is rhythm, there is growth, there is beauty. The Fibonacci sequence continues to inspire not just mathematicians and scientists, but artists, dreamers, and seekers of patterns in the unknown. It is a pattern without end, an eternal spiral into the depths of space, time, and wonder. The golden spiral is one of the most mesmerizing and elegant patterns found both in nature and mathematics. It is not merely a visual curiosity. It is a gateway into the deep structures that seem to govern the growth of life, the formation of galaxies, and even the aesthetics of beauty itself. At the heart of the golden spiral lies the golden ratio, an irrational number approximately equal to 1.618. It emerges when a line is divided such that the ratio of the whole to the larger part is the same as the ratio of the larger part to the smaller. This subtle proportion, known since ancient times, has been revered by artists, architects, and philosophers for its seemingly divine harmony. But the golden spiral is not drawn directly from the ratio. It is generated by placing quarter circle arcs within a series of adjacent squares, whose side lengths follow the Fibonacci sequence. Each square grows in proportion to the sum of the two before it, and from this recursive pattern, the spiral begins to unfurl. The result is a shape that expands, yet never quite escapes itself. It winds outward, growing larger with each loop, but never changing its essential form. This constancy within expansion is perhaps what gives the golden spiral its uncanny grace, a balance between change and permanence. Nature, it seems, has discovered this pattern as well. The spiral shape appears in sunflower seed arrangements, in the unfurling of fern fronds, in the spiral shells of nautilus mollusks, and even in the arms of distant galaxies. Each instance is a quiet testament to the universality of this curve, appearing where growth occurs in constrained yet efficient ways. But the golden spiral is more than a pattern. It is a suggestion that beauty, structure, and order are not merely imposed by the mind, but are already written into the unfolding of the universe. It asks us to consider whether the forms we find pleasing are shaped by evolution, or whether they reveal something deeper, something intrinsic to the geometry of existence itself. As we trace the curve of the golden spiral, we are not just following a mathematical line. We are stepping into a tradition that spans centuries, across disciplines, cultures, and even species. We are witnessing a symbol of growth, of proportion, and of an ever-deepening mystery. A spiral that expands infinitely outward, yet always remains connected to its center. The tesseract, also known as the hypercube, is one of the most mind-expanding and enigmatic objects in the realm of higher dimensional geometry. It is the four-dimensional analog of a cube. Just as a cube is to a square, the tesseract is to the cube. But unlike its lower dimensional counterparts, the tesseract cannot be fully visualized in our three-dimensional world. It belongs to a realm just beyond our direct experience, a space where geometry stretches into a fourth spatial dimension. To understand the tesseract, we must begin with a familiar process. Take a single point, extend it in one direction, and you have a line. Move that line perpendicular to itself, and you create a square. Take that square, extend it upward into the third dimension, and a cube emerges. Now imagine taking that cube and moving it in a direction perpendicular to all three of our spatial dimensions. A direction we cannot see, or even properly imagine. What arises from this abstract motion is the tesseract, a figure that exists not in our physical space, but in the landscape of mathematical imagination. The idea of a fourth spatial dimension has long fascinated mathematicians, philosophers, and artists. It challenges our deepest intuitions about space and reality. How can something have a direction that is beyond up, down, left, right, forward, and back? The tesseract lives in this mystery. Its structure contains 8 cubic cells, 24 square faces, and 16 vertices, each perfectly symmetrical, each related to the cube in the same way a cube relates to the square. In art and science fiction, the tesseract has become a symbol of higher realities, gateways to other dimensions, or representations of the infinite complexity of the universe. In mathematics, it's not just a curiosity, but a powerful object of study in fields like topology, theoretical physics, and multidimensional algebra. Just as the shadow of a cube cast onto a flat surface reveals only a distorted, two-dimensional projection of its true form, so too can we only glimpse the tesseract through its projections into our 3D world. These projections often appear as interlocking cubes, one inside the other, joined at the corners by lines that seem to stretch and twist impossibly. And yet the tesseract is not an illusion. It is a logical, coherent structure governed by the same principles of geometry that define a line or a square. Its reality exists within the consistent fabric of mathematics, and perhaps, in some deeper dimension of the universe itself. What makes the tesseract so beautiful is not just its complexity, but the way it invites us to expand our minds beyond the familiar. It asks us to contemplate the very limits of perception, and to imagine spaces we cannot enter, but can describe, understand, and even explore through thought. The tesseract, like so many objects in higher mathematics, does not just exist in space. It exists in possibility, in our dreams of transcending the visible, in the quiet contemplation of symmetry, abstraction, and elegance. It is a reminder that reality may be far richer and far stranger than we are able to see. The Sierpinski Triangle is one of the most elegant and enduring symbols of fractal geometry, a realm where complexity emerges not from chaos, but from astonishingly simple rules. First described by the Polish mathematician Wojciech Sierpinski in 1915, the triangle is not a single shape but rather a recursive pattern, one that continues to reveal itself at smaller and smaller scales, no matter how closely you look. It begins with a single triangle. Then, from the center, another triangle is removed, dividing the original into 3 smaller ones. This process is then repeated infinitely on each of the resulting shapes. What remains is a pattern of eternal subtraction, a delicate lacework that is at once perfectly ordered and infinitely complex. But the wonder of the Sierpinski triangle goes deeper than its geometry. It is a visual expression of self-similarity, a property found not only in mathematics but throughout the natural world. From the branching of trees to the ridges of mountains, from the delicate filigree of snowflakes to the structure of galaxies, nature itself seems to favor this recursive elegance. And yet, the Sierpinski triangle, with all its beauty, emerges from nothing more than a rule repeated over time. What makes it especially remarkable is that despite its infinite complexity, the area of the triangle tends toward 0. As more and more triangles are removed, the figure retains its shape, but not its mass. It is in some sense a ghost of a triangle, ever present in form, but vanishing in substance. A paradox not unlike those found in the foundations of quantum theory, where particles may be said to exist in multiple states, and where reality itself flickers between being and becoming. It also invites us to reconsider the boundaries between the discrete and the continuous. Though composed of clearly defined parts, the Sierpinski triangle possesses no single dimension we can easily assign. It exists somewhere between 1 and 2 dimensions, a fractional dimension, known as a fractal dimension, a space that is more than a line, but less than a plane. And perhaps this is what draws us to it. It whispers to us of a deeper order, one that hides beneath the surface of what seems ordinary, a sense that behind every shape, every curve, every cloud in the sky, there might lie a hidden rule, simple and recursive, giving rise to beauty beyond comprehension. The Sierpinski triangle is not just a mathematical object, it is a meditation, A quiet unfolding of infinity, shaped by subtraction. A reminder that even emptiness can be structured, and that in the quiet recursion of pattern, we can glimpse something eternal. The Penrose Triangle, also known as the impossible triangle, or impossibility in its purest form, is a shape that defies the logic of three-dimensional space. It was first conceived by the Swedish artist Oskar Reuterswärd in 1934, and later popularized by mathematician Roger Penrose and his father, Lionel Penrose, in the 1950s. At first glance, the triangle appears simple: three straight beams connected end to end forming a continuous loop. Each corner looks entirely reasonable when examined in isolation, but as your eyes follow the edges around the figure, a quiet unease begins to form. Something is not quite right. The beams twist and turn in a way that shouldn't be possible. Angles betray depth, lines contradict space. The illusion completes itself in silence, and you are left with a shape that can exist only in the mind. The Penrose Triangle is not a trick of light or shadow, nor a misunderstanding of dimension. It is a deliberate violation of spatial consistency, a shape that cannot exist in our three-dimensional world, yet exists effortlessly on paper or screen. In this sense, it is not merely a drawing, but a philosophical proposition, a challenge, a riddle posed to the nature of perception itself. Why does the mind accept the triangle, even as the eyes sense its impossibility? This shape invites us to confront the difference between what is seen and what is real. It teaches us that perception is not always bound to logic, that the mind can be seduced by patterns that have no anchor in physical space. Much like the EPR paradox questioned the fabric of reality at the quantum level, the Penrose Triangle questions it at the level of space and geometry. Both suggest that reality is not always what it seems, that there are deeper structures at play, sometimes hidden in plain sight. Artists like M.C. Escher embraced the Penrose Triangle and its relatives to construct worlds where waterfalls flow in endless loops, and staircases lead nowhere yet return to themselves. These are not merely artistic flourishes, but meditations on the strange elasticity of perception. In contemplating the Penrose Triangle, we find ourselves suspended in a space between truth and illusion. It is a reminder that not all impossibilities are errors, some are invitations to wonder. The hyperbolic plane is one of the most striking and unintuitive creations in the realm of geometry. At first glance it may seem abstract, even alien, curved in ways that defy our everyday experience of space. But beneath its unfamiliar surface lies a profound elegance, and a deep challenge to our conventional understanding of shape, distance, and form. In Euclidean geometry, the geometry of flat surfaces, parallel lines remain equidistant and never meet. But in hyperbolic geometry, things behave differently. Imagine a surface where, given a straight line and a point not on that line, infinitely many lines can be drawn through the point that never intersect the original. This is the essence of hyperbolic space. It is a world where the rules we take for granted begin to dissolve. The hyperbolic plane has a constant negative curvature, curving away from itself at every point. Unlike a sphere, which bends uniformly outward, or a flat plane, which doesn't bend at all, the hyperbolic plane curves inward, infinitely, and everywhere. This geometry gives rise to strange visual effects. Shapes appear to shrink as they move outward, though in reality, they are all the same size. Circles grow exponentially in circumference as their radius increases. Triangles, no matter how large, always have angles that add up to less than 180 degrees. This geometry can be represented in many ways, but perhaps the most famous is the Poincaré disk model, where the entire infinite hyperbolic plane is compressed into a finite circle. Within this circle, straight lines appear as graceful arcs, bending in subtle, continuous ways. The edge of the disk represents infinity, not as a limit we reach, but as a boundary we can never cross. Mathematically, hyperbolic geometry was once considered heretical. For centuries, Euclid's postulates were treated as unbreakable truths. But in the 19th century, mathematicians like Nikolai Lobachevsky and Janos Bolyai dared to ask, what if the parallel postulate was wrong? Their boldness gave birth to non-Euclidean geometries, of which the hyperbolic plane is perhaps the most hauntingly beautiful. Yet the hyperbolic plane is more than a mathematical curiosity. It is found in nature, in the delicate ruffles of coral, in the growth patterns of lettuce leaves, in the fractal-like structure of certain fungi. These forms arise, not from theoretical abstraction, but from real physical processes: expansion, tension, and curvature. In these natural shapes, the hyperbolic becomes tangible. There's a quiet mystery to the hyperbolic plane. It challenges the intuition shaped by a flat world, inviting us to imagine a reality where space is woven differently. A geometry, not of rigid order, but of graceful deviation. Where symmetry exists, but never conforms. Where infinity is near, yet never reachable. In contemplating the hyperbolic plane, we are reminded that space itself can be more fluid than we expect, that geometry is not fixed, but shaped by the underlying structure of reality. Like the EPR paradox in quantum physics, the hyperbolic plane expands our notion of what is possible, and in doing so, nudges us closer to truths that lie just beyond the reach of familiarity. It is a shape that doesn't just curve space, it curves the imagination. The Klein Bottle is one of the most fascinating and counterintuitive objects in the realm of geometry and topology. First described by the German mathematician Felix Klein in 1882, the Klein Bottle defies our usual understanding of surfaces, space, and dimensionality. It is a shape that challenges not just our visual intuition, but the very notion of what it means for something to have an inside and an outside. At first glance, the Klein Bottle may resemble a bottle with a long, slender neck that curves back and appears to pass through its own side, joining seamlessly with its base. But what makes the Klein Bottle truly remarkable is that in the realm of pure mathematics, it has only one continuous surface. It is a non-orientable surface, meaning that it has no distinct inner or outer side. In essence, the Klein Bottle is a shape that turns in on itself, eliminating the boundary between what is internal and what is external. In our three-dimensional world, constructing a true Klein Bottle is impossible without allowing the surface to intersect itself. Any physical model we create is merely an approximation, a representation constrained by the limits of our spatial dimensions. But in four-dimensional space, the Klein Bottle could exist perfectly, without any self-intersection, without compromise. It is a shape that whispers of dimensions beyond our grasp, of spatial realms we can imagine, but not fully inhabit. This peculiar property, that the Klein Bottle has no edges, no boundaries, no distinction between inside and out, invites deeper reflection. What does it mean for a surface to have no orientation? Can a path that begins on one side truly return to where it started, without ever crossing a boundary? The Klein Bottle suggests that our everyday concepts of direction, containment, and division are not as universal as we might think. In topology, the Klein Bottle is closely related to the Möbius strip, another non-orientable surface. But while the Möbius strip has an edge and can be constructed in three-dimensional space, the Klein Bottle goes a step further, enclosing itself in a continuous loop with no edge, no seam, and no surface to fall off. It is in a sense the natural evolution of the Möbius idea, complete, closed, and infinite in its continuity. The implications of such a shape go beyond mere mathematics. Like the paradoxes of quantum physics or the infinite recursion of fractals, the Klein Bottle reminds us that the universe is not always bound by the limits of our perception. It exists at the intersection of logic and imagination, where space folds, where boundaries dissolve, and where new realities begin to emerge. The Klein Bottle is more than just a mathematical curiosity. It is a symbol of the strange and beautiful structures that arise when we question the assumptions of space and form. It invites us to imagine higher dimensions, to explore beyond the edges, and to consider the possibility that what we see is only a slice of something far more intricate and profound. The Möbius strip is one of the simplest and yet most perplexing objects in the world of mathematics and topology. At first glance, it appears to be nothing more than a loop of paper, twisted once before the ends are joined. But this quiet twist changes everything. First introduced in the 19th century by the German mathematician August Ferdinand Möbius, this shape defies our everyday intuition about surfaces. We are used to objects having two distinct sides, a front and a back, an inside and an outside. The Möbius strip challenges this assumption. When traced with a finger, the Möbius strip reveals its secret. It has only one continuous side, and only one edge. A traveler walking along its surface would return to their starting point, having touched every part of it, without ever crossing an edge or switching sides. It is a surface that turns back into itself, a closed paradox. This strange property gives the Möbius strip its unique identity as a non-orientable surface. It cannot be consistently assigned a notion of left or right, and in doing so, it hints at a world where direction and distinction are illusions shaped by our perception. The Möbius strip has intrigued not only mathematicians, but artists and scientists alike. It appears in the work of M. Escher, where endless staircases and twisted perspectives reflect its logic. It influences engineering, where its geometry has inspired conveyor belts and magnetic tape loops that wear evenly on both sides. But beyond its practical uses, the Möbius strip provokes something deeper. It forces us to reconsider the boundaries we draw between interior and exterior, self and other object and environment. It is a shape that exists in apparent contradiction, and yet it does so consistently, elegantly, and without error. In this quiet loop, there is no clear beginning and no end, only continuity. Only a seamless transition between what seems to be two sides, but is really just one. It reminds us that sometimes, the most surprising truths emerge from the simplest of twists. The Möbius strip does not just challenge our understanding of geometry. It gently nudges us to reflect on the nature of perspective itself, and in its silent symmetry, it becomes something more than a shape. It becomes a meditation. The torus is one of the most elegant and captivating forms in geometry. At once simple in appearance and rich in mathematical depth, defined as a surface generated by rotating a circle around an axis outside the circle, the torus is perhaps most familiar to us in the shape of a donut. But beneath its familiar exterior lies a profound structure that has fascinated mathematicians, physicists, and artists alike. At its core, the torus represents a topology of continuity and return. Unlike a sphere, which has no holes, the torus has a single central void. This hole transforms the way the surface behaves, introducing properties that are both surprising and beautiful. In topology, the torus is classified as a surface of genus 1, meaning it has one handle, a fundamental difference that influences how it interacts with space. But the true intrigue of the torus extends beyond its form. In mathematics, it serves as a building block for more complex systems. In dynamical systems, a toroidal phase space can represent states that loop eternally without repetition, forming the foundation of models in everything from celestial mechanics to fluid dynamics. The torus also emerges in the study of higher dimensional shapes. In string theory, extra dimensions are often curled up into toroidal forms, their hidden geometry influencing the fabric of the universe in ways we cannot directly perceive. Here, the torus becomes not just a shape, but a possible scaffold of reality itself. What makes the torus especially compelling is its role as a symbol. It represents cycles without beginning or end, eternal return, the flow of energy, the passage of time. In many spiritual traditions, the torus has been used to depict the geometry of life, energy spiraling inward and outward in an infinite loop. On the surface, the torus may appear ordinary, but as with many things in mathematics and nature, its true depth emerges only when we pause to look closer. Its continuous surface, its looping structure, its capacity to model both the physical and the abstract, all invite us into a quiet contemplation of unity, motion, and form. The torus reminds us that complexity can emerge from simplicity, and that hidden within familiar shapes are the fingerprints of deeper truths. Like a whisper traveling in circles, it carries with it a quiet elegance, a soft echo of infinity. And in that endless loop, we find not just geometry, but a reflection of the infinite paths our thoughts can take, curving gently, endlessly toward wonder.